70 years ago, humanity discovered a key that could unlock the entire solar system. A technology that promised cheap launches carrying thousands of tons, fast travel across every planet, and even the possibility of journeys beyond our star system. But we chose not to use it. Nuclear power. This wasn't science fiction. Practical, workable designs were already being studied and published by the very scientists who built the Manhattan Project back in 1946. Their research had begun under absolute secrecy, first revealed to the world only as a weapon of terrifying destruction. Now, however, they wanted to demonstrate how it could be used for peaceful purposes. Their proposals would solve one of the most crippling issues of rocketry, the rocket equation. That equation forced chemical rockets to become towering stacks of fuel, with massive, costly sections discarded into the ocean after each flight. Nuclear power could overcome much of this challenge, but not by using nuclear reactors to heat up gases. That would be like trying to drink a swimming pool through a straw, efficient, but never strong enough to lift huge payloads off Earth. The world had already seen the unbelievable force of nuclear bombs, energy equal to tens of thousands of tons of fuel, compacted into a single device. If that explosive power could be harnessed for rockets, it would completely change space travel. But the only way to move a craft with nuclear blasts was to put it directly inside the fireball of an atomic detonation. Most people today would laugh this off as impossible, believing nothing could survive such inferno. But scientists in the 1950s thought differently. This was the birth of Project Orion, and this is its story. The very first problem the Orion engineers faced was simple: what can actually survive a nuclear explosion? The US military had the same question. They wanted to know how bunkers could be built to resist a nuclear strike, and just how strong their own warheads had to be to break through. The radiation, heat, and shockwave from one detonation could even destroy other nukes in the same launch volley, so understanding how close they could be placed together was vital. Nuclear tests were run constantly, with materials placed at varying distances from ground zero. One of these tests produced a curious result, known as Lou Allen's balls. Lou Allen, an Air Force physicist, worried about the supply of tritium, the heavy hydrogen isotope used inside fusion weapons. The first hydrogen bomb, Ivy Mike, had detonated in 1952, and larger warheads were planned, which required far more tritium. Allen knew lithium could be converted into tritium when bombarded by neutrons, so he arranged to have steel spheres, 1 meter wide and filled with lithium material, blasted by a 20-kiloton nuclear device. These spheres, coated in graphite, survived the fireball. Graphite was chosen because it has the highest vaporization energy of any solid, able to absorb immense heat before turning to gas. The results shocked everyone. When engulfed by a 150,000-degree fireball, a thin layer of graphite vaporized into gas, forming a protective shield, while the steel balls were not destroyed. Even more surprising, they were hurled outward like cannonballs by the blast. What if this effect could be turned into propulsion? The idea gained little traction, until 1957, when Sputnik passed over the United States, sparking the space race. Suddenly, new funding was unleashed, and with it came Project Orion. The concepts moved quickly from physics papers into real designs. Orion wasn't just sketches, actual models were built and tested. One prototype was driven upward 100 meters by 6 chemical blasts. Others were subjected to repeated shock testing. Engineers began to draw up full-scale starships, small Orions for the Moon, massive 10,000-ton, Ultra-Orions, capable of lifting entire space stations in a single launch. These ships could cross the solar system in mere weeks or even attempt interstellar voyages within a human lifetime. But among all these designs, one stood out, the 4,000-ton Orion, the first serious proposal. Standing 78 meters tall, this bullet-shaped Titan could lift over 1,000 tons to low Earth orbit, or send 300 tons to Mars and back with no refueling. At a time when docking in orbit had not yet been done, being able to launch whole space stations or complete missions in a single vehicle was revolutionary. According to declassified reports, Orion depended on 4 key elements. First, the nuclear devices themselves. They couldn't be ordinary bombs, they had to be extremely small but very powerful. At the time, the US and USSR were racing to build ever larger warheads, but Orion required the opposite. Smaller weapons lose neutrons too quickly, making them inefficient. To solve this, higher compression was used along with plutonium cores encased in beryllium, which recycled neutrons efficiently. These designs already existed in miniature tactical nukes, like the infamous Davy Crockett, and were adapted for Orion as pulse units. Each pulse unit weighed around 1 ton, producing a blast equivalent to 25,000 tons of TNT. Crucially, half the mass of the unit was a tungsten plate. This plate turned the detonation from a simple explosion into controlled thrust. In Earth's atmosphere, a nuke turns into a mushroom cloud because the air absorbs radiation and expands as heat. In the vacuum of space, a nuke is just a flash of X-rays and particles, deadly, but useless for propulsion. The tungsten plate captured that radiation, vaporized, and expanded into a high-velocity jet of plasma, the rocket exhaust. Using shape-charge techniques, the pulse was focused against the plate, creating an exhaust velocity 10 times higher than chemical rockets. Detonated once per second, these units produced bursts of thrust equal to 100 terawatts, 5 times the entire power consumption of humanity. But delivered as hammer-like pulses. To handle these hammer blows, Orion's second key element was a suspension system. Facing the explosions was a massive steel plate, coated in oil to protect it, slamming back against gas-filled bags. A 27-meter-long suspension arm, packed with springs and pistons, absorbed the shock, smoothing each jolt into a steady acceleration of about 1.25 g, like riding on a bumpy country road. A pneumatic gun in the center fired each pulse unit out the back every second, sealed by shutters just before the plasma wave struck. The third element was storage, disc-shaped magazines holding hundreds of these pulse units, like ammo in a giant gun. Reaching orbit required 600 units. A round trip to Mars needed 1,500. The fourth element was political reality. And this was the part Orion couldn't overcome. By 1958, NASA had taken control of America's space program. They were already pouring billions into Saturn chemical rockets, and Orion threatened to make those obsolete overnight. NASA quietly cut funding, but the military kept Orion alive for several more years, intrigued by its potential. Designs ranged from an emergency command Orion to serve as a nuclear war backup headquarters, to a doomsday Orion capable of carrying a single warhead equal to the entire American arsenal. To modern eyes, these proposals seem insane, but this was an era when soldiers watched nuclear tests from trenches and nuclear engines were tested in the open air. Ultimately, Orion was doomed by treaties. After the Cuban Missile Crisis, the US and Soviet Union signed the 1963 Partial Test Ban Treaty, forbidding nuclear explosions in space. Orion's pulse units, while technically not bombs, were indistinguishable from them. An Orion launch would set off nuclear alarms worldwide. With performance cut by safety redesigns, the program ended in 1965. But the dream never died. Engineers continued refining nuclear pulse concepts. Modern ideas like microfission, using tiny fuel pellets compressed magnetically, and magnetic nozzles could revive Orion in safer, more efficient ways. Such a craft could reach Mars in 10 days or Jupiter in under a year. The obstacle is no longer science, but politics, funding, and mission demand. No space agency will invest in Orion unless it serves a goal too ambitious for current rockets. Until then, the technology waits, a breakthrough frozen in time. Project Orion remains one of the boldest concepts in human history, a spaceship riding the shockwaves of nuclear fire. A reminder that the line between genius and madness, science and politics, is razor thin. And perhaps one day, when we're ready to leave Earth behind for good, Orion will rise again.